seems like we've got a good number of people in the meeting, and I think it's only fair to try and keep vaguely to time. Thank you all for joining us. As ever, if you have any comments, please feel free to record them in the chat, i.e. just type them in the chat, and obviously questions as well. And then we'll take all comments and questions at the end. And if you don't like typing, then I will invite you to unmute if that's your preference. But without further ado, I'd like to hand over to Tim Foat. You can see his various affiliations there, principally as a scientist at Dstl. And Tim has worked for over 20 years in defense and security related indoor dispersion. And obviously the COVID-19 pandemic has really put the work of Tim and Dstl in sharp focus. So it's really great to be hearing from him today, and I shall mute myself and ask that everyone else does and keeps their cameras off just to save bandwidth whilst Tim is talking. So over to you, Tim.
Thank you, Henry. Can everyone see that okay, the presentation?
Yes, I believe they can.
Thank you. So yes, I'm going to talk today about indoor dispersion at Dstl, and then focus on the recent application to COVID-19 transmission. So just trying to get my slide to change. That's it. Yeah. So the content of the talk. Yeah. First, I'm going to talk a bit about why indoor airflow is complex and why that kind of makes it interesting. Then I'm going to focus on what we do indoor dispersion related at Dstl. I'm just going to start by saying a little bit about what Dstl is for those who don't know. So Dstl is a Defence Science Technology Laboratory, and we're an executive agency of the Ministry of Defence. We employ about 5,000 staff, and they're distributed across a few different locations in the south of England. And we are one of the principal government organisations dedicated to science and technology in the defence and security sectors. So after the introduction to indoor dispersion at Dstl, I'm going to talk about the different indoor dispersion methods we use at Dstl. And then I'm going to focus on two examples. So a little bit on the eddy diffusion modelling for indoor dispersion, and then finally the second half of the talk on indoor dispersion and COVID-19. So I was going to start by kind of explaining why indoor airflow is complex. So indoor airflow is complex for a number of different reasons. And some of these are the flow in indoor space is often relatively weakly driven. So compared to outdoor flow, when you can have a strong dominant wind direction, often there's very weak drivers to the flow. And this could be the same in a mechanically ventilated space or a naturally ventilated space. And then second, you can have multiple flow directions. So in a naturally ventilated space, you can have two windows open, a window and a door, and you have flow coming from different directions. And even in a mechanically ventilated space, you're likely to be supplying air from a number of different directions. And because of this weakly driven flow effect, the secondary drivers of the flow can be important, so the thermal effects can be significant. And all these factors together result in airflow that's nearly always unsteady and is typically turbulent. So I've used this little example here to try and kind of show some of the complexity in the airflow. So this is a kind of simple test case that was kind of popularized by Nielsen in the 1990s, and we used it more recently to look at large eddy simulation. So this room is in our case, it was 9 meters long, 3 meters wide and 3 meters high. And air is supplied at the top left and is extracted at the bottom right. We had 10 air changes now, so the total volume around the room is refreshed 10 times every hour. And in our simulation, we released a tracer material on the kind of bottom left part of the floor. So this animation shows results from our large eddy simulation CFD outputs, and it's showing normalized concentration. So the concentration is normalized to the source concentration, and this was on a vertical plane through the center of the room. So fresh air comes in here, and you can see the kind of the tracer being emitted from the source on the floor here. And this kind of points towards some of the complexity. So even in this case, which is actually a more simple ventilation you get in most indoor spaces, you can kind of see the complexity of the airflow, the kind of turbulent airflow coming in. And the picture's even more complicated when you get the kind of the airflow dispersing the trace material that's on the floor. So it's hard to both measure and predict the complex behaviour that we see in these types of spaces. But one question to consider is, do we actually need to worry about this complexity, or can we simplify the problem? And quite often the answer to that question is yes. So looking at another example now to point towards complexity, this was an experiment we did some years ago where we had a kind of reasonably complex room. It was about 25 meters long. We released a tracer gas where this cross is shown here. This was released for 20 seconds. You can see the kind of ventilation. There's vents running along the two sides of the ceiling. These are supply vents, and air is extracted from the back of the room. It's a reasonably low ventilation rate in this room, so it was about 4 air changes an hour. So the total volume of air is exchanged once every 15 minutes. And what I'm showing here is a concentration measured at these 26 different gas sensors and how this changes with time. So you can see the kind of first part of the experiment, so after kind of 10 minutes, so you end up with this very complex behavior. So regions of high concentration, low concentration, kind of rapid changes. But then as you move to the later period, actually, even though this room is complex and the airflow is complex, actually it tends towards a kind of mixed state. So after 10 or so minutes, so around about 1 air change in this case, you end up with reasonably uniform concentrations across the space. So this early period is complex. So you can consider the kind of airflow is complex either at early times or close to the source. So even at the mixed stage, if you had a continuous source, you can still end up with complex behavior close to the source. So it's harder to capture these short-term local effects, but it may be that these aren't significant depending on what the problem is you're trying to tackle. So now looking a bit at indoor dispersion at Dstl. So we're primarily interested in the hazard from chemical and biological agents. And we're interested in buildings because these can be targets for terrorists, and they kind of have a kind of people are confined within the space, and there's a lot less dilution than there is in the outside environment. So we're often required to understand the impacts of hazardous airborne material on indoor environments, to assess the risk and to figure out how we could protect the occupants. And the kind of things we're typically interested in is those short-term deliberate releases or accidental releases. The release could be in the indoor space, or it could be outdoors and be transferred to the indoor space. We're interested in gas and vapor materials and also the aerosol phase. And we typically look at the time-dependent concentration or the integrated dose. And as well as these kind of chemical and biological agents, we're also interested in vapor transport for a detection of explosives. So the environments we're interested in, we're interested in everything really from small-scale systems to complex networks. Our typical interest is non-residential buildings, and we're interested in everything from kind of room scale to whole building scale. And these show some of the examples. So like a large, perhaps an office complex or a small meeting room or a public space. We've also had an ongoing interest in transport, and this could be everything from a single vehicle to recently we've been interested in transmission of COVID on the London Underground, and this was a project called TRACK, which is Transport Risk Assessment for COVID Knowledge. So when you're thinking about indoor dispersion methods, you can kind of split them broadly into 2 categories. So you can have specific approaches and general approaches. So the specific approaches are broadly, if you want to consider what's going on in a specific building or a specific scenario, these models are typically detailed, but they're very sensitive to change. If you change to a different scenario, a different building, you may get very different results. And it's sometimes difficult to base this kind of more general advice on. So the other end of the range is the more general type modelling. So these models are normally coarser, but they're more robust, and these are more suitable for providing advice on. So the different indoor dispersion techniques support one or other of these approaches, or could kind of match multiple of them. So typically experiments or high resolution modelling, such as computational fluid dynamics modelling, are typically kind of supporting this kind of specific advice, whereas the kind of single zone modelling and multi-zone modelling, which I'll talk about in a bit more detail shortly, typically support more of the general approach, and then other kind of techniques kind of span the two. So I'm going to move now through some of the different modelling methods and some experimental methods. So the first one I'll introduce was whale mix modelling. So going back to the experiment we had before with the concentration time series. So I said that even in this room, which is quite complex, after a short period of time, you end up with this kind of mixed condition. So what we can do, we can apply what's called a whale mix model to this environment, which it basically consists of an exponential rise in concentration followed by an exponential decay. And you can see it very kind kind of accurately represents what's happening in the later phase, but it isn't capturing what happens at the early phase. So it's under predicting high concentrations and over predicting low concentrations. So this type of approach, the kind of single zone, it's all based on this well mixed modeling assumption, and the assumption is that anything that's released into the space is instantly and uniformly mixed across the space. This well mixed kind of assumption can be used in a number of different techniques, and the two main ones we use are single zone modeling and multi-zone modeling. So single zone modeling, so as I said, it kind of considers an average concentration in a room or even a building, a simplified building. And it's based on this kind of, this is a simple representation. So you just have a single volume, you have a flow rate of air into the space, fresh air, you've got a release rate into the space. And the kind of, these are the key parameters that drive this type of simple model. You can kind of take this to the next extent by you can include things like, you could include a ventilation system. So you could have contaminated air coming in from outside. You could perhaps have some filtration efficiency in the ventilation system, or you could have a recircling ventilation system. And you could have other things like, you could have lost term, you could have aerosol depositing to surfaces, or vapor sorbing of surfaces. And we've been using these types of models for some time at Dstl, and they're very useful for kind of providing carrying out rapid calculations and providing kind of more general generic advice. Then the next level of complexity with this, using this well mixed type of modeling, is multi-zone modeling. So for this, you can start looking at kind of a whole floor of a building, or even a whole building. So here you have a number of separate well mixed spaces, and you have to define the kind of connectivity between the different spaces. So here we've got a single story of a building, so we've got lift shafts, we've got the main kind of office space, we've got stairwells, and each one of these is a separate well mixed zone. As I say, you define the coupling between the two. You could represent a single story of a building, or you could put these together and you can end up with a representation of the whole building. With this modeling technique, multi-zone modeling, you can calculate the airflow and the dispersion. There's a number of third-party tools available, and the one we use primarily is Contam, which I believe was developed by NIST in the US. There's extensive validation has been carried out for these techniques over the years. And something we've looked at is linking this type of indoor model to an outdoor dispersion model. So these models are very quick to run, but they're still, even though they're simple, they're reasonably complex to set up, as you can imagine, because you've got to define lots of spaces and the interconnectivity, but they're very good for understanding whole building effects. So the next kind of level to take the well mixed modeling to is something that's called state space modeling. So state space modeling is a method where you solve a system of coupled first order differential equations, and you can understand the dynamics of a more complex system. So the way we use it, we take the steady flow field from the multi-zone model, and then use a state space method to predict the dispersion of the material. And the approach we've used most often is producing these things called impact matrices. And what we can do here, so the advantage of these state space models are very quick running. So we can look at the effect of a release in any location. We can look at the effect of release in any location from the release happening in any location. So in these impact matrices, the columns indicate the release location, and the rows indicate the impact location, so the kind of zone we're interested in. And we've got three examples here. So we've got a residential, a 3-story with an attic residential building. We've got an apartment complex, and then a kind of complex healthcare setting. So in this plot here, we've got the so the release locations along the top here. So this is I can just about read that. That's showing the lower floor, the first floor, the attic. And then this is the impact location, so the attic down to the lower floor. And what you can see in these impact matrices, you can very quickly see that if a release happens in the lower floor, it's affecting all the floors up to the. If you have a release in the second floor, it's contaminating the
Tim, just to say that when you're looking off to the left, the microphone is failing to pick up your voice at all times.
Oh yes, okay, yeah, thank you, Henry.
Thanks.
Yeah, so I'll just repeat that. Yeah, so in this example here, you can see if there's a release on the lower floor, it affects the whole of the building. But for releases in the upper part of the building, it's not contaminating the lower parts of the building. And the same effect is seen here for the residential building. So releases on the first floor aren't affecting the higher floors. But then in this more complex building, it's showing that releases in any part of the building are affecting the other parts of the building. So this state space method is a very quick way to understand the more kind of complex building systems. So the next modeling technique I'm going to talk about is computational fluid dynamics. So in theory, CFD can predict what happens in the kind of mixed phase, but also in the complex phase. But even with these high techniques, it's very difficult to predict the kind of precise performance. Even these high resolution techniques would struggle to predict the full detail of these concentration time histories. So computational fluid dynamics, it works by solving the fundamental equations for fluid flow over many computational cells. And the biggest problem with CFD, it's very slow to set the models up and slow to run the models. But they can provide very detailed information on time-dependent dispersion, assuming you have sufficient time to build the models and analyze them. And they're very good for looking at flow within specific rooms and large spaces. So the well-mixed assumption that you're assuming the material mixes instantaneously across the space, that holds when rooms are smaller or they're very well ventilated. So when you get to the large spaces, that kind of well-mixed assumption falls down, and that's when the CFD models, are most useful. And then within CFD, you can also include more complex physics. So you can include buoyancy, for example. So the next modeling technique I want to talk about is eddy diffusion. So eddy diffusion is something that sits between the well-mixed modeling and the CFD technique. So it's based around simple analytical models that can be solved very quickly, but it predicts the spatial variation, the temporal variation in concentration. So if we look at our kind of concentration time series here, an eddy diffusion model would kind of capture the kind of the rising concentration, the decay, like the well-mixed model, but also captures some of this spatial variation. So a bit more about eddy diffusion modeling. So it's often impossible to build and run a full CFD model, and this may be because you haven't got the time available, or you don't have information about the geometry, the detailed information about the geometry or the flow in the room. And so this eddy diffusion approach provides us with a spatial resolution, a simplified representation of spatial resolution. And this is an output from a simple eddy diffusion model. So we've got the dimensions of the room here. So this is a plan view looking down. And we've got the width and the length of the room, and this shows the concentration. And this is the kind of prediction you get from an eddy diffusion model. The technique works on the assumption that there's isotropic mixing on a large scale, and this mixing can be due to laminar and/or turbulent motions. And the eddy diffusion models in their simplest form can just be solved in Excel, for example. And this is a simple example which was produced by Crank in 1979. And this is an instantaneous release of a mass of material M in an unbounded space. And so this can be solved very quickly. So the turbulent diffusion coefficient, or the diffusion coefficient that represent this turbulent or laminar mixing, typically ranges from kind of 10 to the minus 3 meters squared per second to 0.1 meters squared per second. So if you compare this to molecular diffusion, which is typically kind of 10 to the minus 5 or 10 to the minus 6, this turbulent laminar mixing is much larger than the molecular mixing. So people have taken these eddy diffusion models over the years and extended them. So Trivas in 1996 produced some models, as well. Other people have done similar things, produced models that allow representation of the kind of, if you've got your source in a confined space, and this is done by showing image sources. And this kind of animation here shows the effect that as the kind of cloud of material moves towards the walls, you get this kind of image source reflection effect. Others, such as Cheng et al. In 2011, extended the model to include a decay term. So this kind of provides a global decay of the released material. So we've done some comparisons at Dstl, comparing the eddy diffusion models to some experimental data sets. So this is the complex room I showed earlier. So with this asymmetric ventilation, and this is a much simpler test case. So this is a cuboidal meeting room, had a volume of about 250 meters cubed. There was a release of tracer gas in the corner of the room for 180 seconds. This room has mixing ventilation and is pretty well mixed. It's got an air change rate of about 10 air changes an hour, I think. So these are the results. So this, the kind of top row is the simple meeting room. The bottom row is this more complex assembly hall. So what we're showing here, we're showing the concentration time series again. And for each of these, we've got 3 sets of lines, or three lines for the experiment and 3 lines for the model. And what the 3 lines show, they show the maximum concentration, the minimum and the average concentration at each time point from all our monitor locations. And the coloured lines are from the eddy diffusion model, and the black and grey lines are from the experiment. So you can see here in this simple meeting room, actually, yeah, the eddy diffusion model is pretty well predicted. It predicts nicely predicts the rise of the lowest concentrations. It's got the decay phase very well predicted, but it's under predicting some of the peak concentrations. And then even in this more complex space, again, we're getting the decay pretty nicely. It's predicting the kind of minimum, the rise of the minimum concentrations, but it's under predicting those, and it's also under predicting some of the peak concentrations. So all in all, actually, if you can get the right diffusion coefficient, the eddy diffusion model can be very, very useful. But I thought I would also show, if you try to model these same scenarios with the well mix model, the well mix model can do pretty well. So particularly in this simple meeting room, which is pretty well mixed, you see the well mix model actually gets a decay phase very well. So everything that happens after kind of 250, 300 seconds, it's predicting very well. But it is over predicting the lowest concentrations and under predicting the highest. And in the complex space, again, it's doing pretty well in the later phase, but it is under and over predicting in the early phase. So these eddy diffusion models are kind of completely dependent on the diffusion coefficient. It's this diffusion coefficient DE here, which drives the rate at which materials mixed across the space. And historically there's been very limited experimental data for buildings. So some people have tried to produce relationships to define this. So Cheng et al. In 2011 produced an empirical relationship based on some naturally ventilated spaces. And he showed that the diffusion coefficient was a function of the air change rate of the room and the volume. And Drivas and Carlson in the 90s produces turbulent kinetic energy balance models. So they look at the rate at which turbulent kinetic energy is being produced and dissipated. And they come up with quite a nice relationship. And we took this a step further in 2020, and we used a set of CFD models. So what is shown here, each one of these crosses was a CFD model, which we kind of automated the CFD setup. So we ran 250 different CFD models of rooms, different shape sizes. And we showed that by using this TKEB model, but setting the characteristic length scale to the size of the inlet vent, as opposed to the room height, which is what Drivas and Carlson had done, we showed that you could simplify the relationship. So then the diffusion coefficient is just a function of the fresh air flow rate in the room, the total flow rate in the room, the volume of the room, and the number of air vents. So we're also supporting a couple of studies looking at trying to further improve our understanding of how the turbulent diffusion coefficient varies in realistic spaces. So the first one is there's some work being carried out at Southampton University by Dr. Desmond Lim and Dr. Christina van der Wel. And their kind of primary interest is the effect that people movement have on the mixing. So they're using the PLIF technique, planar laser-induced fluorescence, and the PRV technique, particle image velocimetry. They've produced a model that represents a simple space, and this is the same kind of space as showed earlier from the Nielsen 1990 test case. And they've put their model where they can move these cylinders around, which will represent the people movement. They've put this model in a water tunnel at Southampton, and they're going to try and study how the diffusion coefficient changes in this space. This work's funded by the UK Intelligence Community Postdoctoral Research Fellowship. And the second study is at University of Cambridge, and this is being carried out by PhD student Jack Wardale and supervised by Professor Gary Hunt. So Jack's primary interest is the large indoor spaces that are either naturally ventilated, mechanically ventilated, or of a hybrid ventilation. And they've got a kind of static water tank set up, and they're combining they've got a combination of mathematical techniques and laboratory techniques to understand how this diffusion coefficient changes. We've also produced an open source Python tool for eddy diffusion modeling. So this was done with a company called RiskAware, and the tool's called the Rapid Indoor Dispersion Tool, RIDIT. It's available at this link here. It's a simple text-based tool where you just define the size, shape of the room, the diffusion coefficient, where you want the releases to happen, the release type. They could be instantaneous, continuous releases. You can run it in just a single mode or kind of an automated batch mode and get some graphical or text output. And this is just an example of the graphical output. So finally, on the kind of methodology, I'm going to talk just briefly one slide on the experimental tracer techniques. So typically, an experimental tracer dispersion experiment, we'd have a controlled release of the material. This could be a tracer gas or aerosol. We measure the concentrations at multiple locations around the space. And these types of experiments are very useful for us to validate the modeling, but they can also help underpin the development of the models. And then also the experiments can also be used directly to carry out hazard assessments. But the big problem with the experiments that they can be very expensive, and they only really provide measurements for a specific location and condition. So it's more this specific end of the problems rather than the general end. And also it's very hard to monitor large spaces. So if you were interested in a large public space, such as like a kind of station concourse, it's very hard to instrument that space. And also when we're looking at tracer gases, the tracer gas concentrations are a secondary effect. Ideally, we'd know how the air is moving around the space, and then we'd like to know how the dispersion is. So the tracer dispersion by itself isn't necessarily always ideal for validating models. So for the rest of the talk, I'm going to talk about this project where we've been using CFD indoor dispersion to look at the transmission of COVID. So this was a work package within the NCS Protect project. So the NCS Protect project is a partnership between 21 UK academic and research institutes. And the aim of the work was to understand our improving of how SARS-CoV-2 is transmitted from person to person and how this varies in different settings and environments. The aim of our specific work package was to understand and characterise respiratory droplet dispersal in these indoor spaces. And this work we carried out in partnership with the Health and Safety Executive and also the University of Leeds. There's also some colleagues at Dstl have been supporting the NCS Protect project in other areas. So some colleagues have been using the QMRA technique, which is quantitative microbial risk assessment modelling. And this was done to assess potential factors that influence disease transmission in indoor spaces. And then other colleagues have been looking at touch transfer, so how efficiently COVID is transmitted to and from surfaces. So for our work, we were particularly interested in how temperature and humidity affects this airborne exposure. So the test scenario we used was the one I've talked about earlier, this simple meeting room that has mixing ventilation, air is supplied and extracted from the ceiling. In our model we had an air change rate of 5 per hour. There was no recirculation within the ventilation system. And we ran the model at 3 temperatures, so 16 to 28 degrees centigrade, and through relative humidity 30 to 70%. The person was coughing in the room, and each condition was averaged over 5 coughs, and each cough was followed by a 5-minute mixing period. There was no face coverings worn by the person. And we applied the same methodology that had been previously developed by HSE and is reported in this paper by Koldrick et al. And in this previous paper by Koldrick et al, their methodology was validated using this experimental data from Public Health England, now called the Health Security Agency. So in our model, the person coughs into the space, so that the cough exhalation introduces a number of droplets into the room. There's a number of different ways to kind of define the cough droplet distribution, but we chose this model by Johnson et al, which is called the BLO model, the bronchiolar laryngeal oral model, and it's shown here in simplified form. So this is droplet diameter in microns against the number count. So these 3 modes end up producing what they show to be a 2-modal distribution. And then the kind of angle at which the person coughs into the room and the velocity of the cough was based on some work by Gupta et al. From 2009. So this person coughs into the room, and their exhalation contains this kind of carrier flow, cough carrier flow jet contains humid air and droplets. Within our model, we modelled the thermal effects from the body, heat from the body and the exhaled air. The turbulence was represented using the K-Omega SST model, which is a kind of standard model used for indoor airflows. The heat from the body, we had 25 watts per square metre heat from the body. We only represented the convective heat flux and not the radiative flux. To model the droplet transport, we used the Lagrangian particle tracking model. This was a fully coupled model, so the carrier flow imparts momentum to the particles or droplets and vice versa. Our droplets evaporate with time. The droplets were just represented as water droplets, but with a non-volatile core. So the idea is the water droplets can evaporate till they get down to this solid core. And we did previously run some of our models with a more complex droplet, where the vapor pressure of the droplet was based on the concentrations of the salts, etc., within the droplets. But we chose to simplify the representation of the droplets here to enable us to run the models more quickly and allow us to model more scenarios. Then we looked at the number of droplets, the number of viral RNA copies within each droplet were based on the viral load in the respiratory fluid and the Poisson distribution. So this little animation just shows an example. Yeah, the kind of person coughing, the cough lasts 0.4 seconds. This shows the droplets are coloured by diameter. So you can kind of maybe just about see the kind of the larger droplets are kind of fired out at the front of the cough jet, but quickly settle out, whereas the smaller droplets are kind of more rapidly slowed by the static air in the room. So within the model, the person was standing 3 meters from one end of the room, and they were coughing and kind of down the long axis of the room. The airflow was supplied from the vents in the ceiling, louvered vents, and these louvered vents supply air at 30 degrees to the ceiling. And this forces the air to travel along the ceiling and down the walls, or the kind of two jets meet at the intervent boundaries. And the flow is initialized in the room before the coughing starts. I've just got some example output from our models here. So the first set of images here show the particle tracks. So this shows the tracks of individual droplets as they move into the room, and they dry down to become particles. I'm showing the droplets here. We split the data into 3 kind of core size bins. So the first set of these green particle tracks are droplets less than or equal 20 microns, and this is initial wet diameter. The middle set of data is droplets between 20 and 100 microns, and the third set is the droplets greater than 100 microns. So because they've got this non-volatile core, they very rapidly dry down to this solid core, which ends up, the final diameter ends up as 0.3 times the initial diameter. So looking at this data first for the small droplets, it's very clear to see that the small droplets remain airborne and spread kind of across almost the entire of the space. It's interesting, actually, there's a small part to the left of the room where, just because of the ventilation makeup, actually it's not well mixing fully to the left of the room. The larger droplets aren't that affected by the room airflow and deposit out very quickly, but the intermediate droplets are perhaps the most interesting ones. So these start out, can be up to 100 microns in diameter, but they dry quite quickly to the smaller size, and this allows them in many cases to remain airborne. So you can kind of see here, as the cough jet, some of them do deposit out, but other ones kind of mix up into the airflow in the room, or of course caught in the thermal plume around the person and are carried up to the space. These blue rectangles on the top of this image represent the room vents. And another point I wanted to make is that, two points. One, there aren't the same number of droplets in each size bin, so we're releasing less small particles than small particles. So it looks like the small droplets are mixing thoroughly across the space, but we're also releasing more droplets, so the effect is emphasized there. Yeah, there's also lots of intercough variability. So this shows results from one cough. So one cough maybe went straight forward and it's quite symmetrical. Another cough may be quite asymmetrical and go off to the side of the room. So what I'm showing now is the viral exposure, and this data is averaged across our 5 coughs. So the viral exposure is calculated from, we look at the location of the droplet, the amount of RNA that's in the droplet, and how long that droplet stays within the computational cell. So each of these, it's a plan view on a horizontal plane at 1.4 meters, and showing RNA exposure in copies seconds per meter cubed. And we've grouped it in a similar way. So we've got the small particles, the intermediate, and the large particle sizes. And so we ran at 3 temperatures and 3 humidities. Results here are for the hot dry case, so 28 degrees centigrade and a relative humidity of 30%. So if we first look at the small sizes are quite well dispersed around the room. But as these droplets are very small, so many of them won't contain any virus at all, and some of them will contain perhaps one or two viruses. The largest sizes, which will contain the largest number of viruses, are too heavy to travel very far from the affected person. So the bulk of the exposure is carried in these intermediate sizes. And if you look, the intermediate, so the cross represents where the person is. The intermediate sizes, you can see in front of the person, some people are still receiving moderately high exposures, 3 meters from the person, and around the sides of the room, even a number of meters away, people could still receive a high exposure. Then if we look at the effect of temperature and humidity, so what we're showing here is again the three large size bins, and what we've got is we've got decreasing temperatures, so going from 28 centigrade down to 16 centigrade. And then we've got increasing humidity, so from 30 to 70%. So in these images, as you move from the bottom left plot to the top right plot, we're having less evaporation. So the kind of original thinkings for kind of when people have done similar studies to these before, you want your droplets to evaporate less. So as you exhale a droplet, some of the droplets are quite large. If they don't evaporate, they're going to fall out the air more quickly, and the people will be exposed less in the room. Whereas conversely, if they evaporate, they can stay airborne for longer and they're going to produce more of a hazard. So what we're showing here is similar to before. We're showing the exposure on 1.4 meter planes and these different conditions. So again, we're seeing very little kind of exposure from the large droplets, and these are shown on different scales. So we've kind of got, this is showing kind of 10,000, whereas for the small droplets, the maximum exposure is only 100. So again, most of the exposure is carried by the large droplets. But it appears from these, due to the unsteadiness of the airflow in the room and the resulting variability from the dispersed droplets, it's not clear from these that the temperature and humidity is having that much effect on the kind of spatial pattern of exposure. So what we then went on to do was look at the exposure from in another way. So we've looked at box and whisker plots. So what we've got the person standing here, they're coughing into the space, and we've looked at three 1 meter cube volumes going from in the direction of the cough, and then each of these is split into these 0.125 meter cube volumes, and we're then plotting the distribution of exposure across these subvolumes. So for those of you who aren't familiar with box and whisker plots, the line represents a medium, the edges of the box represent the 25th and 75th percentiles. The whiskers represent plus or minus 1.5 times this interquartile range, and then the outliers at any points that are outside of this range. And then what we're showing here is the first box. So this is showing all the different temperature humidity conditions. This is the exposure. The red bars represent the first volume, the second the blue volume, and the third the green volume. And so kind of some of the points to notice here are, in this first volume, we're ending up with a very large range of exposure. So we've kind of got 6 orders of magnitude exposure. So depending where someone is located in this first volume, they could be receiving a very high or very low exposure. By the time the kind of droplets, so the droplets are exhaled here, by the time they've moved kind of out of the first volume, lots of the droplets have evaporated and they're becoming more affected by the room airflow. So they're becoming more uniformly mixed in this space. So this is why we're kind of getting tighter distributions. And then by the third volume, nearly all the larger droplets and the larger the intermediate sizes have fallen out. So the air is being diluted as well. So we're ending up with lower exposures in this third volume. So then what we've done now is broken down the exposure into the distance from the person, the temperature and the humidity. So first look at the distance from the person. So we've got the three regions again, the first volume up to 1 meter, the second up to 2 meters, and the third up to 3 meters. And you can see here that there's no statistically significant decrease in the median as you move from the first volume to the second volume. So here it's showing the kind of 1 meter social distancing would have very little effect in this case. But as you move to the third volume, there is this significant decrease in the median exposure, and also the whole distribution is shifted down. And in fact, we're getting a factor of 200 reduction in exposure. And I should say that these exposures are based on 2 people talking face to face. If you had other people in the meeting room, or people kind of off to the side of each other, you'd end up with a more complex picture. Then we've looked at the effective humidity. So what we're showing here is we've got the 3 humidities. So we've got 3 volumes again, the 3 different humidities, 30 to 70%. And what we showed here is we get a statistically significant decrease in the exposure as the relative humidity is increased. But this effect is very small in kind of absolute or relative terms. So you can see there's very little actual decrease in this exposure. But the overall effect is what's been reported before. So for a number of years, so starting with Wales in 1934, people have produced kind of simple analytical models, typically of a single droplet, and they showed that they were seeing these effects in these simple droplet models. And people have done CFD as well, where they've represented a number of these processes, and we're showing a similar thing. But what we've tried to do in our modelling is do a more kind of realistic representation of all the kind of complexity in the airflow. And then finally, looking at temperatures. So interestingly here, we were getting a mixed effect with temperature. So in this first volume, as you increase the temperature, you're getting an increase in exposure. But if you look at this third volume, an increase in temperature here resulted in a decrease in exposure. So we were getting these kind of positive and negative correlations. So this was a result we weren't expecting, but it shows that any effect that temperature is having on the droplets is being overridden by this kind of the complex turbulence and air movement in the space. So to conclude the this NCS CFD study, so our results have shown the importance of the kind of standard government guidance, which is the importance of wearing face coverings, so to reduce the amount of droplets that are exhaled and reduce the amount that are inhaled, and maintaining social distancing. Both these should help to reduce the inhaled dose. And then the conclusions of our work, so I'll just go back to show, yes, the point I wanted to make here is that, so if we increase the relative humidity, the droplets evaporate less slowly and they fall out the air. So this reduces the airborne exposure. But the opposite effect of this is if we're reducing the airborne exposure, we're increasing the deposited materials. So if you had a desk in your space, someone was sitting or standing by a desk, yeah, if we're reducing the airborne exposure, we're kind of promoting the deposition. So you end up with more deposition on the surface. So this could have a negative effect, that it could increase the foamite transition, the foamite transmission. And people have also carried out some studies to look at the effective relative humidity on foamite transition. And my understanding is that relative humidity can increase the efficiency with which material is removed from a surface. So what we're doing here is very much only looking at the kind of fluid dynamics effect of the transmission. So the other effects we haven't considered, so it's possible that temperature and humidity could affect the physiology of both the infected person and the susceptible person. So as I say, this is very much a fluid dynamics effect only. But in this space, which is kind of a generic type mechanically ventilated room, we showed that high relative humidity there was a slight reduction in inhaled dose. But for practical purposes, consideration should be given to the increase in the probability of foamite transmission. And we showed that as the effect of temperature on exposure varied, so we have positive and negative correlations, a comfortable temperature for the space activity could be chosen. And then the final point for this was that based on the kind of small change of the humidity and the complex change of the temperature, we feel that a ventilation rate shouldn't be compromised to achieve either a high relative humidity or a low temperature. And then conclusions from kind of indoor dispersion of interest to Dstl. So indoor dispersion problems for security applications are typically focused on short duration events and often with limited information available. We like to use a wide range of approaches, and this is required in order for us to be able to provide robust advice. And over the years, we've kind of tended to move kind of perhaps from the more specific advice to the more general advice. And this general advice is really useful because it can provide kind of insights into the kind of more general dynamics of the system. And then some of the ongoing challenges we feel is speed versus resolution. So we can have the fast running models, so well mixed models or eddy diffusion models, but we're not getting the resolution that's in the CFD. There's a challenge, do we want to provide generic advice and perhaps miss out some important details or the specific advice? Validation for large indoor spaces is difficult. And ideally we'd be able to monitor the airflow and the dispersion, and this would be tracer dispersion, tracer gas and aerosol dispersion. There's particular challenges around naturally ventilated spaces where you can have kind of quite weak drivers of the flow, and the flow can become stratified, and even CFD can struggle to predict these types of flows. We'd like to be able to include more complex effects, so the movement of people around these spaces and how they affect the airflow. And also we're interested in kind of coupling models, so coupling to the kind of QRMIRA models, perhaps as we use in the track work, or also looking at how people kind of respond, how do people evacuate in a space once they detect an event. And finally, I wanted to acknowledge colleagues, so some colleagues at Dstl who are involved in the eddy diffusion modelling, and then colleagues who I work with for the COVID project. So this was colleagues at Dstl, colleagues at Health and Safety Executive, and also at the University of Leeds. So thank you, and happy to take any questions.
Well, Tim, I mean, I must say that was a genuine masterclass in the presentation of the modelling of indoor dispersion from the simplest of models up to the most advanced. It was really a joy to listen to, and actually, not unsurprisingly, you presented so clearly. I can't see any questions in the chat. So if people do have any questions, will they just raise their hand? Otherwise, I'm not sure I have a question per se. I mean, well, it is a question, but it's not necessarily about what you presented. I mean, you presented such a nice body of work. Oh, here we go. I'll shut up then, and I'll ask Alice Handy to ask a question.
Hi Tim, thanks very much for a very interesting talk.
Thank you.
I had some questions about your eddy diffusivity modelling, and I was wondering if you'd thought about including buoyancy in the model at all, or the effect that might have on your DE values you found.
Yeah, so the stuff we've done so far, we haven't. We've assumed it's an isothermal space, but the work Jack is doing is kind of focusing on those kind of buoyancy effects. So he's going to have kind of thermal energy coming into the room from the people. So that's very much one of the things Jack is going to look at. So at the moment, we have a kind of single diffusion coefficient that is isotropic and is uniform across the space. When I think if you have buoyancy, you could have different layers, stratified layers, and maybe the diffusion coefficient is going to vary in these different spaces. So it's very much a simple approach at the moment. But yeah, we would like to be able to include the effects of things like buoyancy. And the other relevant point is, if you are the kind of source terms, we're assuming our source term doesn't have much energy behind it, so it's just kind of moving out uniformly. Whereas if your source term is associated with buoyancy, it's going to be carried more kind of dominantly up into the space. So I think there's buoyancy considerations around the source term and the diffusion coefficient. So yeah, nothing as yet, but hopefully we will have stuff in the future.
Thank you. And is it okay if I ask one more question? I know there's other people waiting. It was another question in that you talked about how you use the size of the vent in term rather than the height of the room for your model, being the determining length of scale. And I was wondering, obviously you're using more mechanically driven flow in the experiments and CFD you were doing, and then the eddy diffusivity. Yeah. Do you think that the height, say, of the ventilation in a naturally ventilated room, such as the Cheng model, would be a better length scale?
Yeah, so in the Cheng model, I think they had kind of open windows, and their model kind of related it to the volume of the room. So I suppose they were showing in their particular case, it was a room. They were suggesting it was kind of dominated by the room scales rather than the vent scale. So whether that's a difference between ventilated spaces and mechanically ventilated spaces, I'm not sure. Or they did a series of experiments on these two rooms. So maybe if they extended their experimental range to more spaces, maybe they would show that the vent size was a critical factor. So it's just in our spaces, we looked at mechanically ventilated spaces with ceiling mounted vents, and it just was, we got a better correlation when we use this, the length scale related to the vent rather than related to the room height. Yeah,
and physically it makes sense in terms of turbulence generation, but yeah, excellent. Thank you so much.
Thank you.
Stephen Gage.
Sorry, hello. It's a quick question. I'm particularly interested in distributed local air sterilization in COVID-like infections. And I just wondered whether you'd done any modeling, or you're aware of any modeling where local sterilizers are actually in play.
So is that like sterilizer that's using UV or
that's something? It, yeah.
We definitely haven't done any. There's a number of publications out there looking at sterilization. I couldn't point you to any specifics, but I've definitely seen papers where, some people I know have them in kind of located in the top of the room. And some of our colleagues have looked at filtration units and not trying to sterilize, but filtering locally. I don't know, Henry, you might have, whether you know any specifics about whether you've come across specific work looking at local sterilization.
Well, it goes back 100+ years, I think. Most recently, there are trials going on in schools, which Kath Noakes is very involved in. There's a lot of work, is the short. There's been a big study at Addenbrooke's Hospital in Cambridge as well, post-pandemic. And I think the Addenbrooke's stuff, at least some of it is published, I believe.
So it's all in place. That's great. Yeah. Thank you.
And I think if you search, if you search on some of the kind of German academic searches, is Google Scholar, there's lots there. And I suppose if you struggle to find anything, drop me an email.
Yeah, or me, I'd happily put you in touch with people. Clive Beggs is someone who's done a lot of work historically on it. Christine McHugh.
Hi, thank you. Yeah, thanks for your talk. Most workplaces and even meeting rooms, each person is usually accompanied by a computer, and I believe that could double the rate of heat generation. To what extent do you think that would alter your conclusions?
Is that for the COVID transmission?
Yes.
Yeah, I suppose. So I think the kind of effect we were looking at was the effect. So we were changing the kind of air that's being supplied to the rooms being supplied at the different temperatures, humidities. So I think the overall findings would be the same. I think, yeah, the person's got a hot air plume that will mix the space, that will mix into the space, and then you're right, the kind of computing equipment will have a similar effect. So I suppose locally you're getting those kind of thermal plumes, and they can have significant effect carrying the material up into the space. So I suppose if you had a room with lots of people and lots of offices in it, it would definitely be more complex. And my guess would be kind of any temperature humidity effect you've seen will be reduced even further. So I think if you have a really simple space, I think the temperature humidity effect will be more dominant. So as your kind of room gets more complex, I think that temperature humidity effect is swamped by these other processes. So I think, yeah, in a complex office space, I think the effect would probably, my guess would be it would be reduced further.
Okay, thanks.
Excellent. Well, perfectly timed, Tim, a nice amount of questions. And then if we wrap up here, I think we can all have a break before, no doubt, another meeting at 1 o'clock. But thank you so much, Tim. And I can so understand why you have visiting professorships and fellowships, because I would love our students to hear from you as well. So thank you very much. It was a fantastic talk.
Thank you. Thanks.
Thank you.